it's just like the waveform that like how does?
Well, I mean, their sine and cosine curves shifted one way or the other. Yeah, I think I've lost your question there.
Yeah.
Try again.
Okay, so in a normal, like in a DC circuit, you have, let's say through a resistor, you have electrons running through it,
Right.
bumping into things, which is causing resistance.
Correct.
How is that different with an alternating current?
With alternating current, for the resistor, you still have that. For capacitor, you have buildup of charge, which in essence causes the current not to flow smoothly. It's not like I take an AC power supply and just take two wires and stick them into the outlet. I've got the capacitor is causing, it adds another impediment to the current just flowing past it.
The capacitor?
Yeah, by building up charge. So the more charge you build up on the capacitor, the harder it is to get current through it. So there is an equivalent resistance in that, or sorry, there's a resistance. It causes a resistance that we don't call resistance in AC circuits, but, or sorry, DC circuits, but it does impede the electron flow, because if I just took a battery and hooked a capacitor to it, capacitor will get up to full charge and stop all flow.
I guess I'm just wondering what the difference in the electron flow is with an AC circuit versus a DC circuit.
Well, the electrons will be flowing back and forth. That's the big difference. So,
Back and forth with.
as in, for the capacitor, if I started out, this might be the high side and the low side, and then at some point later, that'll be the low side, that'll be the high side.
Whereas in a DC circuit, it's always going in the same loop.
Yes,
Okay. So they're all constantly flipping back and forth with an AC.
yes.
So it's not doing going around.
No. Now, this was the source of a huge battle 100-some years ago. And there were deaths involved. Europe is on DC primarily because their communities are much closer to each other. And the United States is so huge that we have much more space that we need to send stuff out over. And it turns out that there's much more power loss in a DC circuit, in a DC system than there's in an AC system, at least initially. The way DC power plants are set up now in Europe, they offset that issue. But because the DC circuits in Europe, or the power supplies, the current's not running, it's not like the current's running like that. The current does fluctuate and take advantage of.
So we could have done it too and accounted for the power loss?
At the time, they were not being done that way.
Yeah.
Because,
But now we probably could.
yeah,
Too late.
what allowed us to be able, so for AC, there's less power loss, and that's thanks to the transformer. Invented by
What?
Tesla.
Oh.
Really?
Yeah. Now, Tesla didn't make much money off of it. George Westinghouse did. George Westinghouse saw that he had a good thing there, so he got the invention, realized AC and the power it could have with AC circuits. Edison, on the other hand, he was a huge proponent of DC, and if the US had gone DC, Edison would have made a mint.
Didn't Nikola Tesla get passed over on multiple things though? Kind of like forgotten by history in a lot of ways on the discovery.
Yes,
Yeah.
yes. I think he died a pauper, or at least poor. George Westinghouse saw it, took advantage of it, made a fortune off of it.
Yeah.
Now, one of the
Poor Tesla.
Yeah. So there's this big contract at Niagara Falls of whether it was going to be a DC power plant or an AC power plant. There's a battle back and forth. When I said deaths were involved, Edison wanted electrocutions to happen with AC current because he wanted people to associate AC with death.
Oh, dang.
Ultimately, I think efficiency won out for the time.
What does that have to do with Niagara Falls?
They were putting a hydroelectric plant there.
Oh.
Wait, so being more efficient on
For long distances, shooting power over long distances, AC has less power loss.
And we mostly use DC.
We use AC
We
here.
use AC.
Our power, the outlets here are AC.
What's like one way you use it? I can't picture,
Of what?
like an AC power supply, like what would that be used in?
Everything.
Like everything, what do you mean?
All of our outlets are
Oh,
alternating current.
Your cars are DC though,
Really?
right? Cars are DC.
Probably. I mean, you can get converters. I mean, if you go to Europe with your electronics that are set for US standards, you can buy a converter which will convert the AC into DC.
Oh, so that's why we can't like bring most like hair dryers and stuff into
Yeah, that, and also they have a different
different outlet.
different outlet and a different maximum voltage. All right,
That
so
sucks.
let's actually talk about that for a moment. What's the voltage here?
120.
So you just said it?
120.
All right. If my voltage is constantly oscillating back and forth, what is 120?
The amplitude.
It is not.
Frequency.
It is not. What is our frequency, by the way?
I forget.
All right. So US standard frequency is 60 hertz.
That was gonna be my guess.
And if you did voltage, 120 volts. But that 120 is actually an average of sorts. So let's just take one cycle of power, and again, I'm just gonna assume cosine. So if that is my voltage, should use lowercase e there. If I found the average value over one cycle, well, you find the average by adding a bunch of stuff up and dividing by what you got. What would the average be?
0.
What was that, Paul?
0.
Yes. Why?
Because as soon as you have one max positive, you also have one max negative.
So if I'm gonna find the average here, I mean, clearly, if this is voltage, AC voltage, and I stuck my multimeter into that outlet, it's not showing me 0. So how do they get an average if the average is actually 0?
Absolute value.
They could have mathematically, not necessarily the simplest way of doing it. What they did is they square it, then find the average, and then take the square root. So sort of in reverse order, you do the root, you find the mean, and you square it. This is known as the RMS value. So let's have fun with the RMS value. Assuming it's just a simple cosine curve, so V is equal to epsilon cosine of omega t. And first off, what's the period? Not one.
1 over 60.
No.
2 pi.
That's if it were just cosine of t. What's that omega do?
So it's just omega, is that what you just said?
Omega.
Would it just be omega?
And 1 over there.
No, it's 2 pi omega.
Did you say 2 pi omega?
Yeah.
Let's combine bits and pieces of several answers. Pi over omega. That's the period.
Yeah.
I believe that came up before.
Why is it like that?
If you imagine an air is spinning at an angular speed of omega. If omega is 1, then it's going to take 2, if it's 1 radian per second, it's going to take 2 pi seconds to get all the way around. If omega is 2, so I got a 2 sitting in front of here, it's like this thing is spinning twice as fast. So as omega goes up, this is spinning faster and faster, which means the time it takes to go all the way around is getting smaller and smaller. That's sort of a conceptual version. Or I want to know at what time am I back to where I started? Well, I'm back to where I started when omega t is equal to 2 pi, or t is equal to 2 pi over omega. That's the point at which I'm back to where I started. All right, so I have that right there. Let's find the root mean square value. Gonna have some fun with calculus here. So I want to square it. So I have epsilon squared cosine squared omega t. I want to find the average. Well, if I'm finding the average, if I have some function f of t, the average value of f of t is going to be the integral of f of t over the integral dt over the integral dt. That's the essence of, is that mean value theorem? Remember mean value theorem? That too long? Okay. Should not have been too long for mean value. So to find the average value, I'm going to do the integral epsilon squared cosine squared omega t over the integral dt. And I want to do it for just one cycle. So from 0 to 2 pi over omega. And then from, is epsilon, not epsilon, epsilon. Ooh. Oh, that's right. From time, that's also dt, so from 0 to 2 pi over omega. There we go. So the hard part of this is, what's the integral of cosine squared? Remember, we are physics, we are not math.
I'm looking it up, don't worry.
There we go.
You guys think you need copper reduction?
I don't have the reduction formula written down.
You said you don't, or?
I only have the reduction formula down.
Oh.
Direct integral. Unfortunately.
You go to an integral table. Let's see, there we go. Oh. I did it the long way here. Dang it. Sorry. You're looking it up, Ferris?
Yeah, it says integral of cosine squared is x over 2 plus sine 2x over 4.
Plus sine 2x over 4.
Yeah, plus c. Is that right?
You
That should,
almost. It will be a sine.
this is the integral of cosine squared x, I assume.
Yeah, it should be hold on. Sine 2 omega x
Oh,
or 2 omega t
so sine of 2 omega t.
over 4 omega.
The whole thing?
Yeah, whole thing of sine. And then the x, which is should be t over 2.
Sine omega t?
Just t.
Just t.
If you're to do it the full thing, it'll be sine t omega 2 over 2 plus omega t all over 2 omega, which then would simplify out to that.
All right, but this works.
Yes.
All right. The bottom one, I got that. So that's going to be 2 pi over omega. That's epsilon squared there. So the integral of that is going to be t over 2 plus sine of 2 omega t over 4 omega from 0 to 2 pi over omega. So this piece right here becomes pi over omega plus, then we stick that in there, we get sine of, the omega's gonna cancel out, I'm left with 4 pi over 4 omega minus sine of 0 over 4 omega. That's 0. So in the end, I have epsilon squared pi over omega divided by 2 pi over omega. Omegas cancel out, pi's cancel out, I'm left with epsilon squared over 2. So we've done the average now we do the square root. And so my RMS value, the RMS, is equal to epsilon over the square root of 2. So the 120 volts is our RMS value. So 120 is equal to my amplitude over the square root of 2, or the epsilon, or the amplitude of what's coming out of here is 120 times the square root of 2, which is 169. Something like that. 169.97. How's that sound? All right, someone's about to tell me if I'm right or not. Didn't even write it down. There's one other piece we need to hit, or are we on time? Okay,
Point 7056.
What is it?
0.7056.
7056. And that would be volts. What about omega? I said that the frequency of our outlets is 60 hertz. So the power is being generated by basically something that's turning around 60 times a second, but that's not omega. How do I find the annular frequency if I know what the regular frequency is?
Times 2 pi.
So the annular frequency, 2 pi times the frequency, so 2 pi times 60. And we get 300. Is this the 369.9? Is that where it comes in? There's something that's 0.9.
376.99.
There we go. And that would be radians per second. So our power supply, if I had to write a formula for it, or just wanted to for fun, the voltage of our US power supply coming out of these outlets is going to be 169.7056 volts times the cosine of 376.99 radians per second times time plus some phase shift. And the phase shift is if we hooked up the LabQuest differential voltage probe, stuck it into the outlet, you know, the phase shift is determined by the point at which you start.
So will there be times that we have to go through this process and agree on a problem? Like,
Well, at least some of it.
Okay.
I mean, it's not uncommon for me to tell you the regular frequency, to give you that, and to give you the RMS value. Figuring out this bit right here, the square root of 2, no. If you know it's square root of 2 there, then run with it. You ready to put all the pieces together? Feeling pumped? I say all the pieces. You ready to put the pieces of this with the pieces of the thing that we just did?
Yeah.
There we go. Enthusiasm. It's contagious. So going back to our capacitor, resistor, resistor, so we got R, C, epsilon. Let's assume this is coming out of our power supply. So let's make the resistance 100 ohms, and let's make this, I might change this later, 50 microfarads. Let's see if these are the values I want to keep. I want the capacitive reactance and the resistance to be on this roughly same ballpark. My capacitive reactance is 1 over omega C, which is 1 over omega, which we found is 376.99. My capacitance right now is 50 times 10 to the negative 6th farads, and that's radians per second. What do we get?
$53.0518.
Units?
Seconds over radians farads. Feels weird.
That is not incorrect. That's fine. There is a one-word unit.
It's not,
Think back to our Ohm's law equivalents. What would be the units of the EMF? Current?
and
Resistance?
So,
So volt is an ampere ohm. Over here, that's still volts, that's still amperes.
just ohms.
So 53.052 ohms. Typically, when you multiply, when you have radians times something, you don't write the radians. Nothing wrong with writing it, but typically the radians is not written. So you can make a claim that a second per farad is equal to an ohm, or the unit of time of the classic ohm farad.